All right, everybody, welcome back. Let's get started. Today is the day that you find out how your brain works. Unfortunately, we're not quite there yet. But next best thing, you'll find out how backpropagation works. And in order to do that, first we have to see how gradient descent works for a perceptron before we go on to the more complex case of multi-layer perceptrons. So as a brief reminder, here's where we left off last time. Here's the model that we're trying to learn for the moment, right? Remember, a neuron is a linear combination of its inputs, right? A weight times each of the inputs. Passed through a step function, but we took out the step function to make things simpler. And now all we have is a linear regression. The output is W0 plus W1 times X1, etc., etc. Okay? And we want to learn the weights that minimize the sum of the squared errors. So it's a linear regression, right? So the sum over all the examples in the data set D, in the training set, of the target value, TD, minus the value that is output by the perceptron, i.e. this one, squared. Okay? So if we can make these all very small, that means that we have a very good fit to the data and we probably learned a good model. Okay? Now how do we do this using gradient descent? Remember this diagram? Right? This plane is my weights, and here I just have two weights for simplicity, but in reality I could have millions. And this is my error as a function of the weights, and it's a parabolic surface. Okay? It's very smoothly. It has only one global optimum, very nice thing, right? And we start out with some random, initial weights, let's say right here, right? And so this is our initial error, and we want to get over there to the minimum, okay? And the way we're going to do that is by finding which is the direction of steepest descent here. Let's say it's this, right? And then we take that step, take a small step in that direction, and then we do the same thing again. And so little by little, we finally wind up at the minimum, at which point all steps are up, right? And we stop. Okay?
Yeah. Is it true that these always have global minimums? I thought there was possible to get to low.
No, absolutely. So in general, a function might have lots of local optima, and in fact, that's what's going to be the big problem in backpropagation when we have multi-layer perceptrons. But for now, we're just dealing with a single perceptron where, remember, the output is a linear function of the weights, and the error is a quadratic function of the output. So the error is a quadratic function of the weights, meaning it's a parabola, meaning it only has one optimum. Okay? So how are we going to find this direction of steepest descent? Right? This is where the calculus comes in. Right? That direction is the direction of the gradient. And what is the gradient? The gradient is just a vector, and each component of that vector is the derivative of the error, the partial derivative of the error, with respect to one of the weights. Okay? And the way you find the partial derivative is you keep all the other weights constant, and then you use your good old rules of calculus, which is what we're going to do next. Okay? So this is what we're going to try to do. And then our training rule is just that my change in weights is minus, remember minus because we want to go down in the gradient, not up, eta, which is the learning rate, that determines how big of a step we take, times the gradient. Okay? Or if you look at this one component at a time, like we did for the perceptron training rule, the change in one weight is just minus eta times the derivative of the error with respect to that weight. Okay? So the bottom line is, we need to figure out what this derivative is, and once we've done that, we know how to learn perceptrons using gradient descent. Okay? Any questions so far? All right, so let's do that. Haven't you missed calculus? Remember those good old days of college when you had calculus to take? And you thought you were free of it forever, but now it comes back to haunt you in machine learning, and other things too. But the good news is the calculus that we need for this is not that painful. So let's do it, right? So I want to compute the partial derivative of the error with respect to the ith weight. Okay? So here's my expression of the error, right? Please interrupt me at any point if you have questions or you're not, or you're missing a step. Okay? We're actually going to do this here for two reasons. One is, it's a nice exercise in its own right, but another one, maybe even a more important one, is that we're laying the groundwork for backpropagation. To understand backpropagation, you have to understand this first. That in some ways is the bigger reason for looking at this. Okay? So let's start with this simple case. Okay? So the derivative of a sum, right, is the sum of the derivatives, right? So I can push my dwy inside here. Okay, everybody agree? Okay, very good. And now remember, what we have here is a quadratic function, right? And we're going to use the chain rule of differentiation. Can anybody remind me what that is? My calculus is rusty too, so I need help here. What's the chain rule of differentiation? It says that, let's do that here in the corner. D dx of f of g of x, right, of a function of x is
d of f of g of x with respect to d of g of x times
very good.
d of g of x with respect to d of x.
Yep. Everybody agree? Or anybody disagree? If you don't remember, you don't disagree, right? It's the safety of amnesia. Okay, right, so let's apply that here, right? So my f, right, is td minus od squared, right? And then my g is td minus od, right? And what's the derivative of x squared? 2x. And that is the devious reason why we put this half here, right? You might have been wondering why we divided the sum of squares by 2, right? Why is that factor of half there? It's not needed. It's there on purpose so that it will cancel with this 2 to make the final expression simple. Okay? So here is 2, right, times the function, right? This is the df dg, right? Now dg dx is the derivative of td minus od with respect to wy. Okay? So now, what is that? Let's see, step 1. Let's replace OD, which is the output of the perceptron on the dth example, right, by its expression. Okay, everybody with me so far? The expression of OD, remember, in a very compact form is just the dot product of the weight vector and the input vector, right? So all that we did from here to here was replace OD by the dot product of the weight vector and XD. Okay? XD itself being a vector of, some number of components. Okay? Okay, very good. So now what is this expression? Can anybody tell me? So it's the derivative with respect to Wy of TD minus this dot product. Okay? So what's the answer here? First of all, what's going to happen to TD? What's dwy of TD? 0, right? It's a constant. Now here's the more interesting part, right? What's dwy of w dot product x? Right?
Depends on whether the w is the...
Remember, right? Let's actually go back and look at our expression, right? This is our expression, right here. Right? And I want to find the derivative with respect to wy. Like, for example, let's suppose that I wanted the derivative with respect to w1, right? What would that be?
Just x of 1.
Just x1, right? Everybody agree? And so, and what would be the derivative with respect to xn, with respect to w1? Just gave it away. Xn, right? So in general, the derivative with respect to xi is, to wy is? Except for one small detail, which is what? This minus sign here, right? So it's going to be minus xi. Okay? Everybody agree? And hey, this is our expression. That was easy, right? So what is the derivative of the air with respect to a weight? It's the sum over all the examples of the difference between the target value for the example and the output of the perceptron in the example times minus the value of the corresponding feature in the example. Okay? Simple enough. And this is how we're going to train perceptrons using gradient descent. So we're going to do the same general type of idea. So as before. So we initialize all our weights to some small random values. There's a lot of magic in neural networks in initializing with small random values. We will see later why that might be the case. And then we do the following until we converge, right? Meaning the weights aren't changing by more than 10 to the minus 4 or something. Okay? Here's what I do. I initialize my delta wy. This is the amount by which I'm going to change the weight in this iteration. I initialize it to 0. And then I run through the training examples. I input the example to the perceptron, right? Present it at the input and, get the output, right? And then what I do is I compute my delta weight using the expression that I just saw, right? And then finally, I add up all these delta weights, and then at the end of each sweep through the examples, I change my weights by that amount. Yeah.
In a perceptron, there are a number of inputs,
Mm-hmm.
and then there's this one threshold input that comes up from. Does the threshold input follow the same training rule as the rest of the weights?
Yep, it does. So let's look at that as an exercise, right? So you see this W0 here? This is what you're asking.
One times the threshold, right?
Yeah, so this what we're going to do is we're going to pretend, because this makes it a nice dot product, right? We pretend that there's an input x0 that happens to always be set to 1, right? That's correct. And so that also tells you what the gradient is going to be with, what the partial derivative with respect to this W0 is going to be, right? It's going to be minus x0 blah blah, which is just minus 1. Other questions? Okay, so we have here a very nice little method for learning perceptrons. And it's an alternate method. So anybody have questions about any of this?